Welcome to the course on Introduction to Electrical Engineering. We will have a lecture 24 today on operational amplifier part 2. Starting from presentation of outline, we will talk about today voltage follower, then summing amplifier or summer like a difference amplifier, or we call it differential amplifier. We will talk about integrator and differentiator, the operation which we normally use in many cases. Earlier we were using all these operations in digital analog computers. We will talk about active filters which are realized by operational amplifier, like you can call it low pass filter, high pass filter and band pass filter. Then we will offer some numerical problems. So, with the coming example here, real life applications with the instrument amplifier, you can just see the circuit, how it is the gain defined for instrument amplifier and how is the PCB for this instrumentation amplifier configuration as a evaluation board. Like the other example is the operational amplifier application in ECG, which you take it, and these are the nodes how it is taken to the system through typically in the circuit, and where operational amplifier is used for this detecting and filtering through high pass and filters, so that you can detect the ECG of a recorded from the human being. Like then operational amplifier application in measuring is typically the strain. You take from convert mechanical quantity by transduction to electrical, and then you amplified it, and it goes to finally through this typically either measuring or for using for some application. Then the PID controller in analog form. So, you have a proportional term, you have a input error between reference and the feedback, then you have a derivative part of it, and then integration part, and all three you add it in a summer. So, that you get it at the output, amplified output for a PID controller, which makes the integral portion makes the steady state error 0. So, this in real time we use the PID controller for closed loop control. We use of course PI controller and PID control also. There is a specific benefit. We do not use proportional control much, because you cannot get a steady state error 0, but by adding the integral action, the integral constant makes the steady state at 0, but the derivative, or you can call it the differentiation here, provide the, you can call it the damping also in this output of the PID controller. So, it is used in many process, this PID controller, closed loop process in electrical engineering, chemical engineering, many process, what mechanical engineering. So, a lot of systems where we use the PID controller in analog form, and this is a representation how we represents the analog form. You use hardly 4 operational amplifier are shown here, but this can be done even by single operational amplifier also. Then the another is the temperature controller, which I told you how you can have a in temperature controller, this controller for air conditioning or water heater or in refrigerator, and you use certainly the operational amplifier chips for the control of this temperature in all these applications. Like then your current to voltage converter and voltage convert to current converter for different applications. Like you might have a signal as a current signal, but you have to convert into voltage signal, which you might be giving to ADC to pass on to the process, or you might be having a like a typically a voltage signal coming from the some process and convert into your equivalent to current signal. Like then the voltage follower. So, this is the circuit output which follow the input voltage, and gain is unity here because of this feedback here. So, you have been given negative feedback, but signal is applied to input. So, output is equivalent to input, just the benefit of it is follow the output like. So, a voltage follower or buffer circuit provides a means of isolating or isolation an input signal from a load by using a stage having a unity gain. Why it is so? It offers a no phase of polarity inversion and act as a ideal circuit with very high input impedance and low output impedance. Like so, it does not load your input signal, and certainly the output is also not affected because you have a 0 output impedance. Practically. So, here it is you have a buffer isolate the loading effect. So source you do not take any current from the source, almost 0. So, because it offers almost infinite impedance. So, no current is down from the source, and the load side output you do not have any impedance at the output. So, there is no voltage drop, so you get the signal as it is, but it provides the isolation between input and output as a voltage. Then it is a summing amplifier. A summing amplifier is a operational circuit that combines the several input and produces the output which is weighted sum of the input. So, you can see all the there are 3 inputs here with the RF resistance with respect to the your ground here, and the output is VO equal to minus RF upon RA into V A plus R F upon R B plus V into V B plus R F upon R C into V C. That is the output, which is sum of all three with of course negative sign, with the typically R F provide the gain, and you can have this all resistance equal of normal. So, you will get a addition of all three quantity as output, like of course with the inverted sign. Similarly, you can have here, this is how you can explain the KVL at node V. I 1 is equal to I A plus I B plus equal to I C, and the currents here are given I A equal to V A minus V upon R A. Similarly, I B V B minus V upon R B, I C equal to V C minus V upon R C, and here I 1 equal to minus I F. So, from this you can have typically V A minus V upon R A plus V B minus V upon R B, V plus V C minus V upon R C equal to minus V minus V upon R F, and from this of course, you can do the calculation, and finally, in the same node way. So, you get because V and both are 0, virtual 0. So, you can say minus V upon R F equal to V A upon R A plus V B plus R B plus V plus R C, and that is you can call it V O equal to minus the derivation which we explained earlier, equal to minus R F upon R A into V A plus R F upon R B into V B and plus R F upon R C into V C, and this we call it kind of summing amplifier. Application of the summing amplifier is digital to analog converter. So, accept the input from digital or binary value at typical 0 volt for 0 bit, and we reference 1 for bit 1, and provides the output voltage proportional to the decimal equivalent of the input binary value. So, for example, is considered DAC with the digit of 4 bits. So, here we take it typically in this case to convert this, because all quantity may be 1 or 0. So, we have to take these resistances again in the typically in binary manner, starting from your here typically R 4 is like if we say 2 R 3, similarly 4 R 4 and 8 R 1. That is the way how we call it most significant bit and least significant, the weightage of them, and in general it is taken R n equal to 2 n minus 1 R 1. So, and then we have a feedback. So, we add all this with the proper weightage. So, we will get a analog conversion, digital conversion to analog conversion here equivalent, like, and which we call it V A equal to minus R F upon R 1 V A plus R F upon R 2 V 2 plus R F upon R 3 V 3 plus upon R 4 V 4. So, a difference, then another is a differential or difference amplifier. So, difference amplifier is a device that amplify the difference between the two input, but reject any signal common to the input, like, and this is the way how we have a two signal V 1 and V 2, and with the R 1 R 2 and R 4 as a typically a bit and R 2 is a feedback. So, from here you can just get the relation applying KCL typically at V node, negative node. So, V 1 minus V upon R 1 and V minus V 0 upon R 2, and from which we get V O equal to R 2 plus upon R 2 upon R 1 plus 1 into V, that is minus R 2 upon R 1 typically V 1, and from which applying the KCL at V dash, we can say V 2 minus V dash upon R 3 equal to V dash minus 0 upon R 4, from which we get V dash equal to R 4 divided by R 4 plus R 4 V 2, and we say V equal to V dash because they are virtual both same, and then from this you can get a V 0 equal to R 2 upon R 1 plus 1 into R 4 plus R 3 plus R 4 V 2 minus R 2 upon R 1 V 1, and from which we can get V 0 equal to R 2 upon 1 plus R 2 R 1 upon R 2 divided by R 1 plus R 4 R 3 by R 4 V 2 minus R 2 upon R 1 V 1, and from which for difference amplifier we can say we have a V 0 equal to 0, and where when V 1 equal to V 2. So, we can say R 1 upon R 2 should be equal to R 3 upon R 4. So, V 0 will be R 2 upon R 1 and V 2 minus V 1, that give you the output as a difference of the two input, and we call it differential amplifier. So, if R 1 equal to R 2, R 3, R 4, the difference amplifier becomes a subtractor with the V 0 equal to V 2 minus V 1. Now, coming to integrator amplifier, the integrator amplifier is an operational circuit that whose output is proportional to integration of the input signal. So, here you can have the input signal to negative with the R 1 as a voltage source with the R 1 which have a I 1 current, and you have a output with the capacitor feedback with the I C current, and all are typically with respect to the ground, and negative positive terminal is also ground. So, that this both V dash and V are at ground potential and the two currents are equal. So, here you can say V O equal to minus 1 upon R C 0 to T V I lambda dt, and here is the typically the proof of that. So, KCL at the node of V, we can say I 1 equal to I c, because the V dash is at ground potential and no current is flowing to the any other path. So, current can be written as I 1 equal to V I minus V upon R into I c, that is minus C upon dV upon dt, dV 0 upon dt, or you can call it V I minus V upon R equal to minus C dV upon dt, or dV equal to minus 1 upon R c into V I dt, and integrating from 0 to t is necessary always to discharge the capacitor prior to application to a signal, that is V 0 is 0. So, we can say V 0 minus at t minus V 0 0 minus 1 upon R c 0 to t V I lambda d lambda, and which give V 0 equal to minus 1 upon R c 0 to t V I lambda d lambda. So, that becomes the your integrator. So, a differentiator amplifier is a operational circuit whose output is proportional to the rate change of the input signal, that is differentiator. So, we connect a capacitor, that is location we change to realize the differentiator. So, here we say V equal to V 0 output equal to minus R c into d V I upon d t, just to represent the differentiation, and the derivation is here again that both virtually your terminals, input terminals are counted. So, we can say KVL at the V terminal is I c equal to minus I 1, and we can say C d V I upon d t, that is we call it the typically the derivative of the current, and this current coming from I c, value of I c, and the current other current will be your minus V 0 minus V upon R, that is feedback current. Since V 0 equal to V dash equal to ground, that is 0. So, V 0 will be minus R c upon d V by d t, that is the differentiation of output voltage is different derivative of the input voltage. And differentiator circuits are unstable because any fast variation electrical noise with the circuit is aggregated by the differentiator. Now, coming to typically another one like active filter. So, another application of operational amplifier is to build an active filter circuit in electronics to be used in electronics. A filter circuits can be constructed using a passive component like resistor and capacitor, and active filter additionally uses an amplifier, that is an operational amplifier to provide the voltage amplification and signal isolation or buffering. So, typically you can see how the gain with the frequency for high pass. So, here it will block the low frequency, only high frequency is pass, as you can say the frequency band, and for low pass the low frequency is pass and high frequency is blocked, as you can see the characteristic of this for the output upon input. And similarly, here band pass there is a range of frequency through which the output will be available from the input, and for remaining low frequency as well as high frequency both will be rejected. So, these we call it the active filter, from the input signal we get the either the high frequency or low frequency or a band of frequency. So, coming to typically as a low pass filter, typically the diagram is shown here. We have input signal applying for positive sign with the typically R 1 and C 1 network, and we have a gain with respect to gain with the positive like R f and R g. So, at maximum gain will be for this only low frequency will be passed. So, at low frequency near DC, that is f equal to 0, capacitor C 1 acts as a open circuit, and now we get non inverting amplifier. So, we will get A V equal to 1 plus R f upon R g. So, we can adjust R f and R g and decide the gain, what maximum gain we want from this input signal to this, and we say what will the cutoff frequency, the frequency at which the capacitive impedance equal to the resistance at input, gain is 1 by root 2 of maximum, and cutoff frequency comes FOH equal to 1 upon 2 pi R 1 C 1, that is your cutoff frequency, below which only it will pass the your low frequency signal. Similarly, for high pass filter, the only difference is the location of capacitor and this C 1 R 1 is changed. So, at high frequency f goes to infinity, the capacitor C 1 acts as a short circuit for high frequency. So, that signal goes to this and we can get a non inverting amplifier. So, the gain here is again A V equal to 1 plus R f upon R g, we can adjust the value and adjust the gain, and cutoff frequency here is at which the capacitive impedance equal to resistance, at which gain is 1 by root 2 of maximum, and this your cutoff frequency lower side cutoff frequency 1 upon 2 pi R 1 C 1 like. Now, coming to band pass filter, we have to cascade virtually two filters, low pass and high pass filters. First is the typically you can call it the low pass, and another is high pass, and maximum gain is A V equal to 1 plus R f divided by R g, because in both network we have divided A square, and we can say lower and upper cutoff frequency are FO equal to 1 upon 2 pi R1 C1 and FOH equal to your 1 upon 2 pi R2 C2. So, we can decide by deciding the value of R1 C1 and R2 C2, we can decide the range of frequency which we want to pass through this band pass filter. Now, there are some quiz type questions. The first part is the power absorbed by 4 kilo ohm resistors here. So, we can find out the current through 4 kilo ohm resistor is your I equal to 6 volt divided by 4 plus 6, that is 1 milliampere, and power absorbed now it will be I square R 10 to the power minus 3, that is the current square 1 milliampere square into 4000 4 kilo ohm, and that is a 4 milliwatt. Now, the second is calculate the cutoff frequency of first order low pass filter with R1 C1, just keeping the value of FOH equal to 1 upon 2 pi R1 C1, this comes 6.63 kilohertz. Now, calculate the cutoff frequency of band pass filter where R1 R2 is given 10 kilo ohm, C1.1 Fred and C2 equal to 0.002. So, FOH comes 1 upon 2 pi FC 159.15 kilohertz and FOH 1 upon 2 pi R2 C2, that is 7.96 kilohertz. So, this within this band this work as a band pass filter. Now, coming to solve numerical problem, calculate the output voltage of operational summing amplifier, operational amplifier summing amplifier for the following sets of voltage and the RF feedback resistance is 1 mega ohm, where is given V1 1 volt, V2 2 volt, V3 3 volt, R1 500 kilo ohm, R2 1 mega ohm and R3 1 mega ohm, and similarly for B case again V1 minus 2 volt, V2 2 volt, V3 1 volt and R1 200 kilo ohm, R2 500 kilo ohm and R3 1 mega ohm. So, just solving here, putting the value. So, we got the formula here VO equal to minus RF upon R1 into V1 minus RF upon R2 V2 minus RF upon R3 V3, and we will get A case putting the value V equal to minus 1 mega ohm divided 500 into 1 mega ohm divided 1 mega ohm to 2 plus 1 mega ohm 1 mega ohm to 3, that will become minus 7 volt, and second case putting the value V equal to minus 1 mega ohm divided by 200 kilo ohm into minus 2, 1 mega ohm divided 500 kilo ohm into 3, 1 mega ohm 1 mega ohm 1, it comes 3 volt. So, coming to numerical problem 2, find the expression for the output voltage here, assume that ideal operational amplifier and what is the mathematical operation that the circuit operates like. So, here you have a same circuit. So, we can call it, we can use the principle of superposition because it is a linear circuit. So, we can say VO1 with the value of V0 when Vs2 equal to 0. So, V2 will be R upon R plus R Vs1, that is Vs1 by 2, but V2 equal to R1 upon R1 plus R2 VO2, it becomes VO1 will become 1 plus R2 upon R1 into Vs1 by 2. So, let the VO2 be output when Vs1 is 0. So, VO2 will be 1 plus R2 upon R1 Vs by 2 and VO will be total will be your VO1 plus VO2, that is 1 by 2 1 plus R2 upon R1 plus into Vs1 plus Vs2. Now, coming to numerical problem 3. In the DAC digital to analog converter circuit here, RF equal to 10 kilo ohm and R1 10 kilo ohm, R2 20, R3 40 kilo ohm and R4 80 kilo ohm. Because we have to take in binary fashion, obtain the analog output voltage for the digital input of 0 0 0 0 0 1 0 0 1 0 and up to 1 1 1 1. Consider V reference equal to 1 volt. So, now putting the value, the formula here V minus V0 equal to RF upon R1 V1, RF upon R2 V2, RF upon R3 V3, RF upon V4 V4. So, putting the value here of RF and R1 R2. So, it becomes minus V0 equal to V1 plus 0.5 V2 plus 0.25 V3 plus 0.125 V4. So, thus digital input V1 V3 are 0 0, that produce analog output V0 equal to 0 and input V1 V2 V3 0 0 1 give the V0 equal to minus 0.125, and for remaining all 4 combination it comes 0 1 1 0 become V0 equal to minus 0.25 and V0 for 0 1 1 it becomes minus 0.375 and 0 1 0 it becomes minus 0.5 and V0 your all 4 1 becomes typically minus 1.875 volt. So, this is a conversion how we convert from this your digital to analog conversion by using the operational amplifier. Coming to numerical problem 4, design the operational circuit with V1 and V2 and output VO equal to minus 5 V1 plus 3 V2. So, the output of the difference amplifier will be V o equal to R 2 upon 1 plus R 1 upon R 2 V 2 into R 1 plus R 2 R 3 upon R 1 V 2 minus R 2 upon R 1 V 1. So, comparing it with that equation, so we can have R 2 upon R 1 equal to 5 and R 2 equal to 5 R 1, and we can just put the value. So, we get R 3 equal to R 4. So, thus we choose R 1 equal to 10 kilo ohm and R 3 20 kilo ohm, R 3 50 kilo ohm and R 4 20 kilo ohm. Now, coming to numerical problem 5, if V 1 equal to t equal to 10 cos 2 t millivolt and V 2 equal to 0.5 t millivolt. Here find the V 0 t for t greater than 0, assume that the voltage across the capacitor is 0 at t equal to 0. So, we have here the adding the two quantity and then we are integrating it. So, we have V 1 at 3 mega ohm and V 2 equal to 100 kilo ohm with a capacitor feedback of 2 microfarad to find out output. So, you can check with the circuit that the given circuit is a summing integrator with the output equal to V 0 equal to minus 1 upon R 1 C 1 integration V 1 dt minus 1 upon R 2 C integrating V 2 dt. So, V 0 will be your 1 upon 3 into 10 power minus 6 into 2 to power minus 10 power 0 to t 10 cos 2 tau d tau minus 1 upon 10 to 10 1 upon 100 into 10 to power 3 plus into 2 into 10 power minus 6 0 to t 0.5 t d tau, and putting V o equal to, it will become cos become, so it become minus 1 upon 6 10 by 2 sin 2 t minus 1 upon 0.5 t square by 2. So, V 0 is equal to minus 0.833 sin 2 t minus 1.25 t square millivolt. Now, problem numerical problem 6. So, problem is get the output voltage V t for the circuit shown given the input voltage waveform. So, here input voltage is given here the triangular wave with the offset, I mean it goes from 0 to 4 volt, and this is the typically kind of a differentiator circuit as you can see here. So, we can say how it comes. So, the time constant of R c, that is 5 into 10 power 3 to 0.2 10 to power minus 6, it becomes 10 to power minus 3 second, and input voltage given V I equal to 2000 t for 0 to 2 millisecond and 8 minus 2000 t 2 to 4 millisecond. Thus, the output voltage will be V 0 equal to minus R c dV by dt. So, it becomes minus 2 volt 0 to 2 millisecond and 2 volt 0 to 4 millisecond. So, it becomes like kind of a square wave here as you can see here. So, what I mean this, you can call it with the offset triangular wave can become a square wave here by this differentiator. Now, coming to numerical problem 7, A for the input of V equal to 4 volt, find the output voltage V o and current I 0, determine the range of V a for linear operation if the saturation voltage of operational amplifier is plus minus 12 volt, that is the supply voltage like on. So, keeping this here V o will be minus 12 by 4 into 4 plus 12 by 6 minus 10, that is 8 volt, and I 0 will be 8 plus 10 plus 8 by 12, because that is the two resistance are connected. So, that is 1.47 milliampere, and for linear version plus minus 12, that is minus 12 by 4 V a plus 12 by 8 minus 10, that become minus 3 V a plus 20. So, V a equal to 20 plus minus 12 by 3, so it becomes 2.67 volt. It goes V a goes to 2.67 to 10.67 volt. So, numerical problem 8, calculate the V o for the circuit shown here. For a saturation voltage of plus minus 14, find the feedback resistance R f for which the operational amplifier which saturate. So, now we can say typically here the V plus is your 4 by 4 plus 6 into 5, that is 2 volt, and V plus V minus both are same here because they are at virtual equal point 2 volt, and KCL at the minus inverting terminal is here 5 minus 2 by 3 plus V 0 minus 2 divided by 12 equal to 0. So, V o comes 10 volt, and now we can change R f such that the output saturate. So, V a equal to plus minus 14. So, now we can say with the KCL 5 minus 2 by 3 plus V o minus 2 by R f equal to 0. So, R f plus V 0 minus 2 equal to 0. So, R f comes 2 minus V 0. So, to obtain R f greater than 0, use the V 0 equal to minus 14. So, R f is 2 minus into minus 14, that is 16 kilo ohm. That will saturate the output voltage to typically to your plus 14 volt. Now, numerical problem 9, find the V 0 I 0 in the operational circuit, operational amplifier circuit shown here. and in this case taking a figure, this is inverting summer with the 2 input. So, V o equal to minus 10 upon 5 into 2 plus 10 upon 2.5 into 1, putting the value of this all resistance equal to minus 8 volt, and I 0 is the sum of the current through 10 ohm and 2 kilo ohm. So, it becomes V 0 equal to V a b equal to 0. So, I 0 becomes V 0 upon minus 1 by 10 and plus V 0 minus 0 upon by 2. So, it becomes minus 4.8 milliampere. Now, numerical problem 10, in the circuit below R equal to 1 kilo ohm, C equal to 1 microfarad and V 1 equal to sin 2000 t, assuming V 2 equal to 0, find the V 2 for t greater than 0. So, this is just like an integrator circuit like. So, we can say this is integrated amplifier. So, V 2 equal to 1 minus 1 upon R C 0 to 2 V 1 t dt, and thus the V 2 will become minus 1 upon 10 to power 3 into 10 to power minus 6 0 to sin 2000 t dt. So, it becomes 0.5 cos 2 omega 2000 t minus 1. That becomes the typically you can call it the indicating constant here. So, now coming to numerical problem 11, in the differential amplifier shown here, R 1 equal to 10 ohm, R 2 equal to 10 ohm, 10 kilo ohm, R 1 10 kilo ohm, R 2 equal to 10 kilo ohm, R 3 equal to 100 kilo ohm and R f equal to 100 kilo ohm. Determine the output voltage V o if V 1 is 5 millivolt and V 2 equal to 0 millivolt, and V 1 is 0 millivolt and V 2 5 millivolt, and V 1 50 millivolt and V 2 25 millivolt, and V 1 25 millivolt and V 2 equal to 50 millivolt. So, keeping a first A case V equal to minus R f upon R 1 V 1, and that is putting the value, it comes minus 50 millivolt, and second B case V equal to R 3 upon R 2 plus R 3 1 plus R f upon R 1 V 2, putting the value, it comes 50 millivolt, and C case V equal to V 2 minus V 1 minus R f upon R 1, that is minus 250 volt, and D case V 0 equal to V 2 minus V 1 into minus R f upon R 1, that is 250 millivolt. So, there are similarly you can have some unsolved problem given here the way we have discussed in the process, and these are the references from which we build up this all the presentation, and thank you very much.